Hey programmers, welcome back. Right now I want to go over this all tree paths problem. So let's take a look at what this problem asks us to do. So we're going to take in a binary tree. What we want to do is return a two-dimensional array, where every subarray represents a root to leaf path through the tree. So if I look at one of the paths, I must start at the root A, and I can end at any of the leaves. So let's say I first considered the path from A to D. That means I should have a subarray representing the path of the values A, B, D. Right, and then from there, I'll have a similar subarray for every possible path, right? So I could also have ABE. And finally, I can also have ACF. Cool. And in the long run, we want to actually return every path. So we need to be exhaustive here. Previously, I mentioned that for our problems that have us construct paths through a tree, I typically find a depth-first recursive strategy the most natural way to solve this. So how can I go about actually solving this in a recursive way? So let's go ahead and use this as our input tree. And I want to start with always a base case, right? I know in this problem, they ask us to end a path at a leaf node. And so I'm going to need to translate that into a base case. So I need a base case about hitting a leaf node. And I know in general, that's really easy to code, right? A leaf node is just a node that has no left child and has no right child. So let's say I had the generic case. For a leaf node like the D node, what should it return? Well, it's really important to keep a consistent return type for your data, right? So I know in general, my function needs to return an array, right? Where every subarray represents a path. If you interpret a leaf node as if it's its own subtree, a subtree containing just a single node, then what it should return is an array filled with an array of D, right? So bear in mind here that the inner subarray represents the path, right? And the outer subarray represents the collection of many paths, right? So there's only one path through a tree containing a single node, and that path is just that single node itself, right? So I'm going to have this D node return a 2D array filled with its own value. And that base case is probably the trickiest part of this problem, right? How do I know to actually nest another set of brackets around the path? It's all about just thinking about your base case as if it's its own input. And I would have similar return values for all of these leaf nodes. Of course, they would return their own respective values within their subarrays. Now, how can I use these subresults to reconstruct the results at my parent? So let's say I was evaluating this B node, right? I know this B node is going to receive all of the paths from its left child to a leaf and all of the paths from its right child to a leaf. And so I'll just return up these two arrays. And then from there, I'll just combine them, right? So if I concatenated these two arrays, it would end up looking like this, right? Every subarray still represents a path. However, I need to actually add some data into these subarrays, into these paths, right? What I should do is take my current element of B, or my current value of B, and add it to the front of each of these paths. It should end up looking like this. And what does this logically represent? Well, if I look at the subarray BD, that represents the path starting at B and going to the leaf of D. In a similar way, I have path BE. So notice I'm able to check for correctness even before I've hit my top level solution. So this is feeling pretty good. Let's do something similar for that C node on the right-hand side. What you might notice is, looks like the C node has no left child. We actually didn't talk about that yet. So let's say I explicitly drew this null pointer or null node. I'm going to need to add a base case for this, right? So in addition to leaf nodes, I'm going to have to write a base case for null nodes. And I think in general, if I have a null node, then I should return just an empty array. And what does that represent? Well, if I have a null node, logically that represents an empty tree, right? What are all of the root to leaf paths of an empty tree? Well, there are none, right? Because there's not even a root and there's not even a leaf. So that's why I return just a one-dimensional empty array, because there are 0 paths. If I had any subarrays in there, then that would mean I would have at least one path. So that's why it's a 1D empty array. So I'm going to jot down that return value. So whenever I make a recursive call on null, then I should return an empty array. And now that gives me some information to actually reconstruct a solution at C. I'm just going to bubble up these two subarrays. And then from there, if I concatenated them together, I would just end up with still an array containing the path of F. And then from there, what I need to do is add my current value of C into that subarray path. So now I have CF in there. And I'll just maybe format these so it looks a little similar. Kind of like that. Cool. Now we're ready to compute at our top level root. I'm just going to bring up these two subarrays. And then I just concatenate them together. So far I have 3 paths, but all of them need A inserted at the front of all of them. So I take my current value of A and put it at the front of all of those paths. And that should actually give me my final answer, right? If I do a quick sanity check, I have the path ABD, ABE, and also ACF. In terms of the complexity of this algorithm, we'll say that n is the number of nodes, and we can say that the time complexity is, I guess, roughly O of n. So I know I'm going to have O of n recursive calls because I have a call for every node of this tree. One thing we'll have to consider when we write the code is actually how we construct these subarrays, right? So we're probably going to have maybe a little more than O of n time. So I kind of say that this is an estimate because I have to construct all of those subarrays, right? And I know that the total length of the subarrays is sometimes going to be more than the number of nodes. So for example, looking at just this literal tree that we have drawn, it only has 6 nodes. But if I look at the, I guess, combined length of my return, it looks like it has 9 in length, or I have 3 subarrays, each of length 3. So it looks like sometimes we'll overshoot the O of n. So we'll talk about that detail, I think, when we walk through the code. It's not really too much of a fuss for now. We can also say that the space complexity is roughly O of n for the same reason. We know we're going to incur at least O of n for our stack space, but if we wanted to also consider all of the space we use to construct the output, it would be, I guess, roughly n, sometimes more than n. All right, so I'm feeling good about this strategy. Give it a shot and try to code it on your own recursively, and if you get stuck, I'll catch you in the walkthrough video.